Today, we will conduct a technical examination of Intel Optane memory. We're going to break down what it is, how it works, and the specific problem in computer architecture it was designed to solve.
This will be our agenda. First, the problem. Then, the solution. Intel Optane and 3D Point. We'll cover its working principle, its applications, its advantages and limitations, and finally, a summary of key points for your review. So before we can understand the solution, we must first have a very clear picture of the problem. This begins with a fundamental concept in computer architecture, the memory hierarchy.
Now look at this diagram. This is critical. At the top, you have your fastest memory tiers, CPU cache and DRAM. They are extremely fast, but they have two major drawbacks: low capacity and a very high cost per gigabyte. At the bottom of the pyramid, you have your mass storage, SSDs and HDDs. They provide massive capacity at a low cost, but with significantly higher latency. The issue, the one we are focused on today, is the large performance and cost gap that exists right here, in the middle. Let's define this gap more precisely. On the left, we have DRAM. It's fast, but it is volatile. When you turn the power off, all data is lost. On the right, NAND SSDs. They are much slower than DRAM, but they are persistent. They retain data without power. This creates a significant bottleneck. The CPU, which operates at DRAM speeds, is often forced to wait for data to be retrieved from much slower, persistent NAND storage. So, the engineering question becomes, how do you bridge this gap? The answer Intel proposed was a new technology called Optane, which is based on an entirely new type of memory media. By definition, Intel Optane memory is a class of non-volatile memory. It's built on a technology called 3D Point, and its entire purpose, its reason for existing, is to fill that performance gap we just identified between DRAM and NAND flash. It is, in effect, a new tier in the memory hierarchy. This graph illustrates its intended position quite well. You can see it's engineered to occupy the space between DRAM and SSDs. The goal was to offer performance characteristics much closer to RAM, but with the capacity and cost profile leaning closer to an SSD. It's a hybrid approach.
Now let's examine the underlying technology. To understand Optane, you have to understand the fundamentals of 3D Point.
Okay, pay close attention to this diagram. This is the 3D Point architecture. It's a cross-point structure, a three-dimensional lattice. Unlike NAND flash, which has to read and write in large blocks, this structure allows for individual memory cells to be addressed directly, at the intersection of these perpendicular lines. This is a critical distinction.
So, that architecture gives us these four key characteristics. First, byte-level addressability. This granular access is very similar to how DRAM functions. Second, it is persistent. It is non-volatile. Third, because of the direct access, it has very low latency, much faster than NAND. And fourth, it offers high endurance, meaning it can sustain a significantly higher number of write cycles before the media wears out.
All right, so with that working principle established, let's look at how this technology was actually implemented. We'll examine its three primary applications.
The first and most common application for consumers was as a system accelerator. In this configuration, an Optane module functions as an intelligent cache. It sits logically between your main system storage, often a slow hard disk drive, and your system's DRAM. The software then automatically identifies and caches your most frequently accessed data, what we call hot data, from the slow drive onto the much faster Optane module. The practical effect of this is a substantial performance improvement. For a system bottlenecked by a mechanical hard drive, this meant much faster boot times, reduced application load times, and an overall user experience that felt much closer to that of a native solid-state drive.
Now for the second application, we move from the consumer space into the enterprise environment, specifically data centers.
Here, the implementation is different. Optane is packaged into modules called Persistent Memory DIMMs, or PMEM. These are physically installed on the motherboard's memory slots, right alongside traditional DRAM. This allows it to operate on the high-speed memory bus, creating a new, large tier of persistent memory. The benefits here are significant. First, you can create much larger memory pools than would be economically feasible with pure DRAM. Second, because the memory content is persistent, system restarts are incredibly fast. Data doesn't need to be reloaded from slow storage. This directly improves application throughput for any workload that is memory intensive.
The third key application builds on this persistent memory capability, and it's in the realm of databases and big data analytics. For large databases, storage I/O is almost always the primary bottleneck. By using Optane as a high-speed storage tier for the hottest data, things like frequently accessed database tables and indexes, you keep that critical data much closer to the CPU, dramatically reducing the time spent fetching it from slower storage.
The result is a direct acceleration of database queries and transaction processing. It enables more effective real-time analytics on very large datasets. And it also reduces latency in data pipelines for AI and machine learning, where data ingest speed can be a major limiting factor.
So we have established the principles and the applications. Now we must analyze the trade-offs. We will summarize the distinct advantages and the inherent limitations of this technology. This table summarizes the trade-offs very clearly. Look at the Optane column. It offers a unique combination of high speed and persistence. However, compare its cost and capacity to NAND SSDs. It is more expensive and offers lower capacity. Compared to DRAM, it is cheaper and offers higher capacity, but it is slower. It was designed to exist in this middle ground.
All right, let's conclude with a rapid summary of the key concepts from this lecture. These are the points you must retain.
Let's review. The problem: a performance and cost gap between volatile DRAM and persistent SSDs. The solution: Intel Optane, a new memory tier based on 3D XPoint technology. Its mechanism: a persistent byte-addressable memory. Its key feature is the combination of DRAM-like speed characteristics with SSD-like persistence. This led to its primary applications in system acceleration, server memory expansion, and database acceleration. And the core trade-off you must remember is its positioning: faster and more durable than SSDs, but more expensive; cheaper and denser than DRAM, but slower. That concludes our technical explanation.